This is Q, and in today's video we are going to try to prove a very interesting inequality that is related to two sets of numbers that are ordered. So here is how we start. So we assume that we have n number that are noted x1, x2, etc. up to xn, and another set of n number that we are going to call y1, y2, etc. up to yn. So as you can see, these numbers are strictly positive and real, and they are ordered. And what we're going to show is that we can find a very interesting inequality based on this number. So the inequality that we are going to prove is the following one. So we are going to show that 1 over n of the sum from I equal 1 to n of xi multiplied by the sum from I, or let's call it j, equal 1 to n of yj. So this product, we are going to show that it is lower or equal than the sum of y equal 1 to n, I equal 1 to n of xi yi. And so the way we are going to prove this inequality is based on an interesting trick. For now, we are going to call this quantity A, and we are going to call this quantity B. And we are going to see, based on another sum that we are going to write, how we can find back these two quantities and how we are going to be able to deduce this inequality. So we start by calling a new quantity that we're going to call C, and this quantity will be equal to the sum for I and j that are between 1 and n. So it means that we are basically doing two sums here, the sum from I equal 1 to n, and the sum of j equal 1 to n. And what we are going to sum two times here is the following quantity, which is xi minus xj multiplied by yi minus yj. Let's take this quantity alone, and let's see how we can rewrite it. If we develop this factorization, we have xy multiplied by yi minus xy multiplied by yj minus xj multiplied by yi and plus xj multiplied by yj. So this quantity C will be equal to the sum from y and j going from 1 to n of xy yy minus the same sum of xy yj minus the sum of xj yi plus the sum of xj yj. So what we are noticing here is that this quantity does not depend on j, and this quantity here does not depend on I. So because of that, and because we are doing a sum over all the j and all the I, we can write that we are doing here the n sum of y equal 1 to n of xi yi. And we can write this because since this sum does not depend on j, we are summing this term n times, and this is why we can write this. Similarly, we can write that this is equal to n multiplied by the sum of j equal 1 to n of xj yj. And so what you can notice is that this I and this j is just a way of indexing the term that we have here, but apart from that, these two sums are exactly the same. Whether we write sum equal from y to n of xi, yi, it's the same as writing sum from j to equal 1 to n of xj, yj. So these two sums are identical, and you can notice that these two sums are related to this sum here that we were calling b. So what we have here is that we can rewrite that here we have 2 multiplied by n multiplied by b. Okay. Now, what about these two sums here and there? Well, similarly, we are going to have the same trick here, that it doesn't matter whether we call one I and the other j. What matters is that we are doing the sum over one index and the sum over the other index. And since the index of the x and the index of the j are completely independent, this sum is exactly equal to summing all the xi on one hand and summing all the yj on the other hand. If you develop that sum, you will multiply all the xi by the yj and all the yj by the xi. So you can see how you can get back this sum. And what we have seen before is that that sum is exactly equal to a that we have here. So at the end, this term that we call c here, and that we have written as the sum of these two factors, can be written as 2nb minus, so there is this term a, and this term a is appearing two times. First time here, second time there. So we have 2a. Okay, so at the end, what we can write is that this term c that we were writing here is equal to 2nb minus 2a. Okay, so why is this equation going to help us? Well, if you take a look at this factorization here, we are going to rewrite it there. xy minus xj multiplied by yi minus yj. So as we said, the set of the xy and the set of the yi are ordered. So we have x1 lower than x2, etc., lower than xn, and y1 lower than y2, etc., lower than yn. So the reason why it's interesting to write this factorization is because you will notice that two things can happen. Either you have the y that is lower than j, and in that case you will have xy minus xj that is going to be negative, and that's because xy is lower than xj, and that's again because y is lower than j. And you will have the same thing for yi minus yj, and that's because you have the same kind of ordering for the x and the y. So when I is lower than j, you have this thing that is lower than 0, and this thing that is lower than 0. And when you are in the case where I is greater than j, what you are going to obtain is that xi minus xj is greater than 0, and yi minus yg is also greater than 0. So again, two cases. Case 1, you are having this quantity that is lower than 0 and this quantity that is lower than 0. And case 2, you're having this quantity that is greater than 0 and this quantity that is greater than 0. But in both cases, either we multiply two negative numbers and that's going to be something positive, or you multiply two positive numbers and that's going to be positive. So whatever I or j you are using, the multiplication xy minus xj multiplied by yi minus yj will always be positive. And so that implies that C is a sum of positive number. So it's the sum of something that is always positive. So the sum of numbers that are always positive will also be positive. Okay, but we have seen before that C is equal to 2nb minus 2a. So we have C equal 2nb minus 2a that is always positive. This, in return, implies that we can get rid of the 2 here. nb is greater than a. And let's go back to what is a and what is b. So we have a that is equal to the sum of xi for I equal 1 to n, and multiplied by the sum of yi for I equal 1 to n. And for b, we are having the sum of xi yi. So we use the n that is also here. So we are having n sum for I equal 1 to n of xi yi is greater than this. So at the end, we can conclude that the sum of xi from 1 to n multiplied by the sum of yi from 1 to n, this divided by n is lower than the sum of xi yi from 1 to n. And this is the conclusion of our video.